All right, next up is my colleague, William Peterson, Bill, from Augustana College, and he's going to tell us about optical path spectroscopy.
All right, thank you, John. And Will, thanks a lot for the description of the PyScope code and how we utilize that at our observatory. I think some of that old non-portable code you mentioned might be some of mine. So, as John said, I'm Bill Peterson, and I probably count as one of those culprits that started this whole thing. I was one of the undergrads in one of those pictures that John showed in his talk. So I have a lot to thank Dr. Mutel for in helping drive the direction of my career as well, and help me to pass this on to the next generation of students that I teach at Augustana. So what I'm going to talk about now is I'm going to describe in detail some of the things about the compact GRISM spectrometers that we use in the RLMT, and particularly the high resolution GRISM that we just developed. Right. So to give the punchline first, this is a picture of the compact GRISMs we've developed being installed into our filter wheel with its custom housing that is 3D printed to provide enough space. And there's, again, some of the information about the capabilities of those GRISMs. So we have a low and high resolution, and the low isn't to imply that this is a less powerful tool. It's just the one we developed first. So when we made the high resolution GRISM, the old one became the low resolution. But the main point of these tools is that they can be built or designed and built at for very low cost. And they're well within the capability of small colleges and institutions to install and use in their own instruments. And we make them available as well for people to use. So the question arises, this is sort of a theme, is like, why would we do these things in most of our talks today? And generally the answer is because we can. But that's the fun thing about having your own small telescope that you share with a small group of people. But so there's, of course, tons of reasons to do spectroscopy in astronomy. It's a lot, we're looking at light, and a lot of what's going on with light is in the spectrum. But I'll just talk about this particular example that one of my students is Emma Motley is presenting in her poster. This is some spectra using the low resolution GRISM of V1405 Cassiopeia, which is a neon dwarf nova, but actually is turning out to be one of the longest decay neon dwarf novas, which makes it rather unique. And so she was able to obtain spectra using our low resolution GRISM and high resolution GRISM. But in order to understand the evolution of an object like this, and particularly the way that it is discovered that this is a neon nova, is by the spectral content, and seeing how it evolves over the years in which the light curve has been decaying. It involves looking at the different abundances and intensities of the spectral lines over time and how those things change. So an important part of having a tool like this at a smaller half meter class telescope is that, as Will said, you have the capability of doing more observations than you would if you had to request time on a competitively scheduled large telescope. And we also, because of PyScope, have the ability to very dynamically to finely schedule observations. So rather than having to request large blocks of time on a given night, schools that have priority can fit in their observations, and if there's time left over, other schools in the consortium can also fit in can continue to monitor this dwarf nova over time, or any number of other sources. So this is why you would want something like this at a small school. So the reality of trying to do spectroscopy at universities like where I work at Augustana is demonstrated by the somewhat extreme example where I tried to get this SBIG DSS-7 spectrometer that was in a closet when I arrived working. And if anyone at another similar school has tried to use an instrument like this, it's just difficult. They're heavy. They're kind of awkward to attach. You have to take things off the telescope and then put it on. So now your camera is not in the right place anymore. And pointing it at the right thing can also be difficult, especially when you have a slit, right? Because you don't know what you're looking at. So I tried something with a flip mirror where I could kind of point the telescope at the star and then flip the mirror, but things move around too much, so it doesn't work very well. So here, as you can see, it's daytime. I was just trying to get a spectrum of the sun. But the main point here is it's difficult, right? So instead, we developed something that can fit directly in the filter wheel, right? So here's the basic idea of the design, right? So you can see the optical path of light coming in, and what creates the spectrum is a diffraction grating. And so it's not uncommon to use diffraction gratings in the optical path of a telescope. But the problem is that because of the way the dispersion occurs, you will get a curved focal plane for the spectrum, right? So you add prisms to bend that spectrum back onto the camera sensor so that it's going directly in the optical path and to remove some of that aberration. So this isn't new science, but what is new is that we've created a way of installing this in a small housing that can fit in a filter wheel that could be 3D printed with ordinary off-the-shelf 3D printers, like you see. So you can see this in the two pictures below. If people have questions about developing one of these at your own school or would like to have help in designing one, feel free to contact us. Our website is probably the best place to reach us. So then to actually install one of these in the filter wheel, most filter wheels don't have a lot of extra space above the filters because filters are flat. So again, though, we can solve this problem by just 3D printing a taller housing for most filter wheels, right? And this is not a difficult design problem to do. Then another issue to deal with, or just to think about, is that because the GRISM has a specific dispersion axis, it's most helpful if the spectrum are dispersed in the horizontal direction on the camera sensor. So we've also, so a lot of filter wheels have tabs like the ones that you see in order to hold the filters in place. So this was a recent addition to our model, was to add these tabs to basically unequivocally fix the dispersion axis of the GRISM so that it would go the right way on the sensor. So to see an example of just how that happens, here's showing basically an extraction of a spectrum from a GRISM image. So on the left, we have just a regular image through an R filter, again, of V14.5 Cassiopeia. And I'll use this kind of as an example throughout what I'm talking about here. But we have the star field here. And then to get your GRISM image, all you have to do is select the GRISM filter. There's no taking things off the telescope and putting on or having some kind of motorized attachment or something. So the other thing is that obviously it's a slitless GRISM, but as Will described in his talk, because we have this recentering algorithm built into PyScope, it's very easy either during robotic operation for the telescope to automatically find the star. So before it takes a GRISM image, it can automatically take a regular photometric image of the sky and recenter, and then you know exactly where your spectrum of interest will land in your GRISM image when you switch over to that filter. You can just extract it from the image. So then once we extract the image, we just need to have a calibration for the spectrum that comes out. You just need to create a calibration by observing standard stars like Jacobi stars. And I'd like to mention that this calibration here, this gain calibration here that we've been using for a lot of our projects that you'll see in the poster sessions was actually obtained by a student, as well as the code that we're using for extraction. So Kane Lukoski did a lot of the work on getting the gain curve and also updating the code in the IPython notebooks that we use to extract this spectrum. So students have a lot of part in developing these tools that we use. So to show some of the abilities of this tool, here is a spectrum of a Seyfert galaxy using this low resolution GRISM. And the thing to look at is we can see this forbidden oxygen 3 doublet, and we can resolve both lines in the doublet and get an estimate of the spectral resolution by looking at the full width half maximum of that spectral line. So having developed that, we wanted to do more. So we developed a high resolution GRISM. So for that, we wanted a denser lined grating. But because of that, that creates larger dispersion. So you need bigger angle prisms in order to get the spectrum back onto the sensor. And you also have to pick what wavelength range you want more specifically. So we went with the H alpha line. So we think we could look at the structure of that line and phenomena like redshift and things like that. So because we were constrained by the height that we had available inside our modified filter wheel, we went with these values for the prisms and lines per millimeter diffraction gradient. So again, here you can see a prism image where you can see the dispersion, and in the extraction image, what I think is interesting to note is you can see the H alpha line, and it's actually a double line that you can see directly in the image. So just to show some examples of the effectiveness of the high resolution prism, here's a spectrum from a Seyfert galaxy where you can see that doubled H alpha line, and the space between those two lines is, or I'm sorry, this is wrong source. This is a VE star, and the distance between the two doubled H alpha lines is half a nanometer in this image. So that gives you an idea of the resolution of this tool. Here's another H alpha prism image showing the luminous blue variable star P Cygni, the earliest one discovered, and we're able to resolve one of the characteristic P Cygni profile lines for the helium line there. So to get an idea of the sensitivity, you can return to this Seyfert source that I showed earlier as the example for the low resolution prism spectrum. So here it is in high resolution. And to look at some archival data from the Isaac Newton telescope, in that image, you can see the H alpha line in the middle, and we can see very clearly that some oxygen lines to the lower wavelength side and sulfur lines directly to the right, to the higher wavelength side. And we can see those in our high resolution spectrum, but we're sort of just detecting them. So that qualitatively gives you an idea of the sensitivity of this prism. So hopefully I've presented this as something, a tool that is useful for small colleges with this class of telescope. But if that doesn't work for you well enough, then you do have another option. In searching through the internet, I did find a user on cloudy nights who developed his own spectrometer using a diffraction gradient you can purchase on Amazon. So that should be very cheap. Unfortunately, even though he was able to get this very high resolution spectrum of a CFL bulb, he says it's too heavy to use on a telescope. So if you're going to have to wait for more development to use that. So thanks for your time. And if there are any questions?